Hello, Shmita.
Yeah, yeah.
I think we should start now.
Okay. Yeah, so hello. Am I audible?
Yeah, you are completely audible.
Okay.
But your screen is not visible yet.
Let me share my screen. I have not shared it. Now my screen is visible, right?
Yeah.
So is this view good for you or this one? Which one?
Actually, it is same, just exactly same like previous one.
Oh, so then this will be good, right?
Yeah, I think it's good.
Okay. So today what I am going to discuss mainly is quantum measurements, and I will mainly focus on the unsharp quantum measurements, which is I feel that uh, this unsharp measurement is quite unsharp in most of the textbooks. So let us start. So let us start by what a measurement, how in quantum mechanics a measurement is defined. So before I start, I will assume that you know a little bit about this linear algebra and some basic matrix operations and quantum mechanical postulates. As I have seen that in quantum computing class, most of these things have been covered. So I'll assume that you know these things. So firstly, let's start a quantum measurement. So, okay. So in measurement process, it involves two things. Like one is our system, which I am going to measure, and what I am going to measure. What means what kind of observable. So let me give a distinction between observable and operators. So observable is a common thing. Before the birth of quantum mechanics, also this observable, this term was there. So by observable, I mean what can be observed by some experiment or maybe by anything. So what can be observed? So a observable in quantum mechanics, as you know, that it is represented by operators and Hermitian operators. So observable in quantum mechanics is represented by Hermitian operators. So when I say that I observe something, so in quantum theory, you do actually you have done a measurement of that operator. I mean, it is represented in by that operator in quantum mechanics, and you get some eigenvalues of that operator, and you say that these are the possible values of that observable that I can observe if I measure that observable. Okay. And the system is actually in quantum mechanics, you basically represented by some wave function psi, and also in general by some density matrix, what is called it density matrix. This is nothing but this outer product of psi. This is my system. Okay. So while doing a measurement, what I am actually doing. So let us now consider this very simple example of Stern-Gerlach magnet. So from here I have something, some electron or some atom I am sending through this Garlic magnet, and there is some magnetic field, say in some x direction. I apply some magnetic field through the magnet, and I pass this electron through this Garlic magnet. So this electron is represented by some sort of wave function, say psi, which is let's say some linear combination of some states, say KI JI. So this is a familiar state to you, right? So superposition state, we basically write it like this. So a general state can be written like this. So let's say this system is represented, this electron is represented by this state. For generality, I have used a pure state here. And there are two things. So one is you want to measure the spin component of some electron. So actually this is your goal. So you have an observable spin in some direction. Your goal is to measure what will be the possible values of spin if you measure that particular observable. But what you are observing, actually in measurement, what you are observing, this is a detection in the screen, right? So it will be either detected, say I separate it by this. So either be detected in this region or be detected in this region. But what was your goal? Your goal was to predict the value of an observable, which is a spin observable. So a property called spin. But what you are measuring, it's a position. It's an observable called position. So you are measuring the position, but your goal was to measure the spin of that particular system. So what jump we are making here? So this is very important while defining a measurement. So what you can observe in your everyday world, that is a position. So spin is a very abstract quantity. So spin you only know in quantum mechanical textbooks, where the spin, you cannot see an electron is rotating or something like that. So that is a theory. In that theory, we assume that this kind of spin kind of phenomena exist in nature inside this electron. So electrons properties can be revealed through this theory. But the spin you cannot see. While you are performing the measurement, you cannot see some electron is rotating. This you can never see. So you associate your unknown thing to a known thing. So your known thing is you can see the position in the screen, position of the electron in the screen. So by observing a known thing that you can see, you have the ability to see where the electron can be detected. So by observing this known thing, you are inferring something about something which you cannot observe directly. So then this position is revealing what spin it can have. So how it is revealing that? So let's see. The electron then, as you know, that there will be an interaction Hamiltonian here when I apply a magnetic field on the electron. So there will be interaction Hamiltonian over here. So it will be evolved. Say that Hamiltonian is U, and it is represented by something IH and something that I am not writing right now. So now consider this electron to be consist of two components. So one component is its spin component. So psi. So let me write psi better. Okay. My pen is not working. One minute. My pen is not working, maybe. Can you hear me?
Yes, we can hear you.
Wait for 1 minute. My pen is not working. Okay. So this electron now has two components. So let me write the overall wave function to be capital psi, and I write the spin component of the electron by small psi ket, and the position wave function by this. So this is just a tensor product of this overall wave function of the electron consists of two things. One is for the spin and other is for the position. So which position it is? So this position, this is the state. This one is the state of the center of mass of the electron, and it is in the position degree of freedom. Okay. So this is now my overall state. So similarly, if I write the unitary, so what will the unitary do? Let me write the unknown term then. So it is the interaction Hamiltonian H, IH, and some more term will be there. So let me write a lambda here, or maybe something else I should write, because later I will write lambda. So let some G will be there. And there will be an operator, say some operator I am measuring, say A operator I am measuring, and this P. Why P? Because P, you know, as you know, that P is a generator of translation. So if the positions are distinct, I am detecting the position of the electron, then I have to generate a translation. So that I am using this P. P is a momentum operator. It is a generator of the translation. And this operator I intended to measure, this operator A. Now, when I am measuring it, so this A operator.
Sumit,
Yes.
what do you mean by you intend to measure operator? I mean, what is measurement?
What is that? Huh?
What is measurement? What you intend by saying
Yes,
this
yes.
statement
So actually, as I said before, that a observable is represented by a operator in quantum. Okay. So the observable, say this operator A is associated with some observable. So here, let's say the spin component, like some sigma X or sigma Z or sigma Y or 7.
So,
yes.
So basically, the operator is connected with some dynamical variable.
Some dynamical variable. Yes.
Yes.
Yes. That dynamical variable is represented by operator in quantum mechanics. So I am writing it like that. So as I have written the state to be a tensor product of 2 degrees of freedom of the same particle, like one is for spin component and other is for position component. Similarly, I am writing the unitary to be like this: tensor product of the spin component observable and the momentum observable, a momentum operator, you can say in quantum mechanics. So momentum operator, that is a generator for translation, as you know. So my unitary is like this, because anyway it has to act upon this whole state. So the dimension should be same. So now, so this A operator, when I write this one, so I can write it like, say, some AI, JI, JI. This is my the spectral decomposition of that operator A. I can write it. So these and AI are the eigenvalues, and these are the eigenstates of that operator. So if I put it into this unitary, so how will be that unitary? So this E can then be written as some I, H, G, A. So A, let me replace it by this. So that will be AI, JI, JI, and cross some P operator. And if you write it explicitly, let me also write it. So this is the exponential term. So you can write it as a series, right? So this will be like 1. So identity plus some this the whole term I, G, H, and this AI, JI, plus P, this which whole square. So first one is 1, then the same term squared by factorial 2 and so on, right? I can write it like this. So as you can see that if I do square or cube of this term, it will return back this one, this because this is a pure state projectors. So it will return back this term, and this term will have the same power as I am doing. Like I am doing square, so it will be AI square, AI cube, and so on. So I will get a similar series that I can write as e to the power something. So then this U will become this JI, and this e to the power minus I, G, H, and say AI. So is it understandable how I am writing this from this line? From this line, how I am writing this one? Is it understandable?
Better to just do the square term calculation.
Yeah. Just I have expanded in exponential series. Then this one will reduce to same one. So it remained, and it will again be exponential. And this operator is now replaced by its eigenvalues.
Sir, there should be tensor cross with that e power I.
Tensor products. Okay, so now see. So the tensor product is not there now because this is a eigenvalue, right? And again, if you consider this whole term as an operator, then you can fix the tensor product over here. But now I am not writing it. That notation is very confusing.
No, still there should be a tensor product, right?
Yeah?
There should be tensor product because in the previous step, tensor product was there.
So that tensor product, I can write it now here, right? Because this E itself is the operator. So here their tensor product won't be there because it is now an eigenvalue, right?
Okay.
Because if you again expand it into E, so it will be a whole observable, a whole operator, right? So I can, then I have to write the tensor product here. Okay, let us write it like that. Okay. So now my unitary became like this. So let us again come back to that state. So now this unitary also consists of this Hamiltonian, that is the interaction between this magnetic field and the property I am measuring. So that spin. So let us see what I can get from this. So my state was this, and cross this phi x. Okay. And also I have written, as you have seen, so I have written this psi to be like this. In the eigenbasis of that operator, what I am measuring. So this is the eigenbasis, right? So let us replace this then. Then u some, say some, let us write alpha I here. That is ai, this is alpha. So some j this and cross phi x. Now, if I operate this u, see the first term. First term is the eigenbasis that I have written this state in the eigenbasis of that observable. This is the eigenbasis, right? These are the projectors. So if I project this whole thing, so let's say this is, I write it j and here I. So what term will survive? Because anyway, these are forming a complete set. So every j I would be orthogonal to each other. So only same terms will survive, right? So then I can write it alpha I j I and this term will survive anyway. G H alpha I is P, right? So let us write a tensor product also. And so phi x will be here. Okay, so one j won't be here. So only one j. Because this j and this j actually is becoming one. So one j will be there, right? So see, this is a state, this is the operator. So now consider this term. So what is this? Only this momentum operator is there and some phi x. So as this generated translation, so then phi x will be translated to some degree of freedom. So this, let's say this. So for example, let's say something, some I x dash and p. If I act it over some, let's say phi x, what will be the state if momentum is the generator? So it will be simply phi of x minus x dash, right? So this term, then I can replace it by that. So now, so then come back to here. So then after this unitary evolution, what it become? I, and this will become some phi of x minus this term, right? So some, let's say g h and alpha I. And what was alpha I? Alpha I was the eigenvalue of the observable I am measuring, eigenvalue of the operator I am measuring. So see what is the joint state? Now this is my joint state after evolution, right? This is my joint state. So it has a spin component and also a position component, but the position is shifted depending on alpha I, right? So phi x minus gh alpha I. Phi is a now function of alpha I, the eigenvalue of the spin operator. That means what? So for any spin value, any spin eigenstate, like say some xi I, the position of the electron will be shifted by some alpha I, that eigenvalue associated with that spin component. So a peculiar kind of state arrive. That means if I observe a certain translation in the screen, from that I can infer what was my spin component of that electron. So this is the important thing. So I'm observing the position of the electron in screen and I am inferring the associated spin component. So this is how the measurement is defined in quantum mechanics. So, so is there any confusion till now? Hello? Hello?
Yeah, no, carry on. If we have question, we'll ask.
Okay, okay, okay. Okay, then remember this thing. So this the joint state of the system. I will come back to this later. This one, this boxed equation. So associated with the each spin component, there is a position component wave function. So I'll come back to this later. So let us now describe the idea of a POVM.
Sumit, before you go there, just
Mhm.
maybe
Mhm.
one thing. Just go back to the previous page.
Yeah.
Yeah, just for clarification, let's say it is a two-level system. Okay.
Right,
So then,
right.
show us the expression. You just scroll up.
Then let me write. So for a two-level system, I will have two eigenstates. So then my psi, this spin psi, let's say psi s, this can be written as say, or let me write summation. I am just removing summation. So this say some z basis, I can write it 1, 1, right? So this 1 and this is -1, right? Into. So these are the eigenvalues and these are the eigenstates.
What you are writing?
Huh?
It should be 0. Why it is outer product form? Acha.
Oh, psi. Oh, sorry. Psi.
Okay.
Okay. Psi yes. Yeah. And the state can be just written as this component. Some S equals to B, like 0 plus 1 by √2, something like this. Okay. So now if after I evolve the state, so it will become something like this. So some 0 into some x0 plus 1 into some x1 by √2. So see, my state was here some alpha I times some xi I, right? So this alpha I also reflected in the final state.
No, so
And
just scroll up. Just scroll up.
this,
I'm not able to, or scroll down. I'm not able to see the last line of that page.
okay.
Not next page, last line. Yeah.
This one. Yeah.
So here in your example, the eigenvalues are +1 and -1. So the position will be shifted towards x +1 and x -1.
X minus
So
1. Yes.
that means if we take x equal to 0 as origin, we will see there will be two possibility of those
Right.
state goes to either x +1 coordinate or x -1. That
Minus.
okay.
So let's say first it was in some x0, then it will be shifted some depending on alpha, because alpha is +-1. So it will be some x +1 and x -1. So 5.
Achha, one more question I just had.
Yes.
So actually that amount of shift depends on the capital G, right? It is the, I think, strength.
Yes, right. It is the
So
strength of the Hamiltonian interaction.
so will you say maybe now or later that if G can be so small that we can't separate between them, then what happen, or what should be the
I'm
G
coming
to
to this point.
separate between them? That kind of question maybe.
Right. This is actually the, if the strength is not sufficient, then we come back to this unsharp kind of. This is the ideal scenario I am discussing now.
Yeah. That in
Yes.
ideal scenario also, that
Huh.
what should be our critical G so that we can separate this x plus 1 and x minus 1 position.
Right. So one thing is sure that more the G, more will be the separation, right?
Yeah, that I know, but how to separate this x plus 1 and x minus 1 position? In your experiment, will those be 2 points, or I think those two will be some distribution, right? Phi of x is some
Yes.
function that you will get
Yes.
some distribution in the field. So how
Yes.
much G should be put so that we can discriminate those two positions completely?
Let's
That
say
question is it
there is
legitimate?
this.
Not, I don't know, but you can.
Yes, it is a legitimate question, and it's a good question actually. So if I apply no magnetic field, so the whole electron will pass through this. So this is the distance, and I am saying the probability over here. So this probability and this is distance. Okay, this axis. So this electron will go there, and this will be a normally distributed graph. But when I applied a magnetic field over here, I will observe two shifts. So like one here and one here, right? So you are saying what will be the critical value of G that will separate these two completely, right?
Yes.
So that can be, that one can calculate by noting all the parameter of the experimental setup, like what is the length of the screen and all these things.
Okay, maybe we can do it as exercise.
Yes, right. One can do it as exercise. Yes. So now consider the same thing. So here what is happening, you observe that for each spin state I have a position state something. So let I arrive to a scenario where this 1-to-1 correspondence vanishes. What happens next? Means like for two state, let's say for two states, say psi 1 and psi 2, there is certain probability that it will come up. Let's say come up for some state, let's say phi x minus some 1. So let's say this is the one detection state. So this is the position state. Let's say these two spin state correspond to the single detection state, means the position state. So what happens then? So this is the question we have to ask to investigate the POVM measurement, which is called positive operator valued measure. And today I am discussing a particular kind of POVMs which is widely used in research these days, that is called spin POVMs. So the question arises from here. To construct that POVM, we have to ask this question. So what happens if this 1-to-1 correspondence vanishes? Means previously what was happening? So this was always going there, and this state was always going somewhere else, say phi x plus 1. This was a 1-to-1 correspondence between the spin degree of freedom and position degree of freedom. So let us consider a situation now, a new situation where this correspondence vanishes. Let us draw one picture again. This is an intuitive understanding of the spin POVM. Later, I will go to a more elaborate physical realization of that. Let me draw this picture. This corresponds to some POVM, say 1. These are projectors. 2. Some I. Set of projectors. And the detection screen is there. So this is a black box. For you, this is a black box. You don't know what is happening inside that. Now I'm describing what is my code. Let me extend it a bit more, unless it will be confusing. So this is the whole black box. And this is the detection. 1, 2. Let's say this is a many outcome experiment. So instead of 2 outcomes, which we are discussing just now, that was a 2-level system. So 2 outcome was there. So let us consider here some k number of outcome is there. It's a k-level system maybe. So in an ideal scenario, what was happening? So from this projector, always I was getting a detection over the first one. So each spin eigenstate was associated with a position eigenstate. So these should come there. And there are some other also. I have not mentioned some from somewhere. So there was a one-to-one correspondence over here. Let's say this one-to-one correspondence vanishes. Let us omit this correspondence. So I don't know what is happening inside. I am only observing the detection. So let's say it is coming like this. I don't know from where it is coming. It is coming from this black box, from certain spin projectors, but I don't know. It may come from any of these projectors. So there are 2 events then. Event 1, that the spin component is projected in the some projector, let's say pi I. It has a probability pi. This pi is the probability that a spin component of some system is projected in pi I. So it is in spin degree of freedom, but the outer one is the position degree of freedom. So this is event 1, and event 2 is the outer one, detection in outer screen, that is some position. So there are 2 events. So now I can ask one question here. Okay, what is the probability that I get a detection at k? So what is the probability of getting an outcome k? So what I should write? Pk. This is the probability of getting an outcome k. I don't know from which projector it is coming. Previously, it was like only from kth projector it should come. But here I don't know. From even pi 1 projector, the kth outcome can occur. So then what I have to do then? Then I have 2 events. So then the whole probability will just be the product of that 2 events. One is pi, that ith projector is selected. And then other probability will be that I get a detection at k when ith projector is selected. And I have to sum over all the I, right? Is this step clear to everyone?
I think yes.
This is very important. If you have any question in your mind, then you can ask. Okay. Okay. Then I assume that everyone has understand this step. So I am asking, what is the probability of getting a detection at k? So this is just product of these 2 events, probability, product of that probabilities. So in quantum mechanics, what will you write? Also use some indices also here. because this is for kth I have written. So in quantum mechanics, what is that? Pi. So Pi, probability of projection on pi I k, this projector, pi 1k or some pi I k. This is just Pi. And what will be this in quantum mechanics? Second one, can anyone say? Let's say I have a state rho. So what will be this probability? I have a state rho, and what is the probability of detection at k? Let's say that is some pi I k. That is the projector corresponding to k, kth outcome. So what will be that? Can anyone answer?
Trace of pi I k into rho.
Trace of pi ki rho, right?
Yes.
Okay. Okay, right. So this pi is a number. So can I do this operation? Can I do this operation?
Sir, it should be square of the trace because we take the mod square of the inner product.
Square of the trace.
Yes, sir.
Why?
Because probability postulate, we see that we have to inner product the corresponding state with the whole state and take the mod square of it.
No. This is whatever you are telling, that is this one. Some psi phi mod square. This is equal to what? Trace of this psi and phi, right? Is this right?
Yes, it will not be a mod square. It's okay.
Yeah. So one is the state description. When you are considering the state, here I am considering the density matrix and operators. So these are related by this equation. Okay.
Yes, basically the confusion is due to one is the Dirac delta notation and another is the operator algebraic notation.
Right.
So when you are writing trace, it is in operator algebraic notation.
Operator algebra notation. Yeah. So this term is very important. This term now, this one. So this is giving me the probability of certain outcome. Previously, what was my probability of certain outcome? So that was like probability of some outcome was written like rho into pi k, right? Now you see that rho is there, but pi k is replaced by some quantity, this one, this thing, some pi times pi ki and the summation over I. This is replaced by that. Why this is coming? Because now there this one-to-one correspondence between this position detection and this spin has vanished. So for a particular detection at k, the viable projectors can be any of the pi I k. There is certain probability pi. So I say this is the spin p of m. This term, what I have written, pi I k, this is called the spin p of m. This is just an intuitive idea of realizing a POV, spin POV. Let me give an example, then it will be more clear. Before that, let me also analyze two of these properties, which in most of the textbook from you already know that this EK should be positive and this should sum up to some identity. Why it is that? So I have calculated this pk, but if I sum over this should be 1, right? So one or the other detection will happen in each run, right? If there is no such experimental error, then in each run, one or the other detection will happen. Then the whole probability will sum up to 1. Then you can just, this sum is over k. You can just replace this by this one, what you have get here. So ek row. So trace of ek row. So as you know from the previous quantum computation class, so this maybe you know. So trace of row is 1. Then what remains? This ek. So what value it can take? Only 1. So sum of ek should be
Sumit,
identity. Yeah.
is it really so straightforward that if trace of row is 1, but does that always need to have ek is equal sum over ek equal to identity?
See, let me write it again then. K trace over ek row. Okay, so I can write it like this. K ek row. So trace of row is 1. So this quantity, what should be the value of this? And also this is 1.
Yeah, I am saying, is it possible to construct any other operator so that if I multiply it with row, it will again, let's say it is row itself. Okay, sum over ek is row itself, and row is a pure state.
Okay.
Then also trace of row square equal to 1, and row is not
Right.
identity. So from there we can't tell sum over ek
Row
is identity.
is not identity.
Let's say row is not identity. Row is a pure state. Hello?
Okay.
Let's say row is a pure state. Okay. And
Yes.
sum over ek is equal to row.
Yes.
Then also your equation satisfies.
Sum over ek is row. And row is not pure, you are saying.
Row is pure.
Okay, row is pure. Then trace of row is 1, right? And
Yeah,
also
that is
row
okay.
square.
Trace of row square is
Is
also
also
1.
one.
So okay.
Yes,
So from there we can construct sum over ek is equal to row.
Right.
Sum over yeah.
Then also trace of
Sum over ek equal to row. So, but you want to argue that sum over ek should be identity from there. That's why I gave you that counter example that it is not always true.
from the positive counter example, but I don't understand the counter example. Can you tell
No.
once again?
What you want to argue? You want to argue
I want
sum
to argue
over-
that this probability is 1. This is true, right? This is coming
Right.
from total
Yeah.
probability 1.
Yes.
And trace of row is also 1.
Right.
This is the density matrix, properties of density matrix.
Right.
Identity. So
Right.
yeah.
Now you write your conclusion.
Okay. So now I'm writing the conclusion is that this ek, the sum over ek should be identity. Unless you cannot you cannot take, like, if it is not identity, say some identity by 4, you get some identity by 4 ek, then you place it over here, some identity by 4 into row, it should be 1. Can it be 1 for any other value of this? Because trace of row should be 1 for any pure state or mixed state.
Okay. No, that is not possible. Let's write your conclusion that sum over ek equal to identity.
Yes, this is the conclusion. Okay. Oh, so okay.
Erase 4.
Right. So let me cut this, and no one will listen. Yeah. So ek equals to then sum over ek equals to identity. This is my first property that I get. 1.
Okay.
Property
Now
one.
I have a question. You write sum over ek equal to row.
Okay. Sum over ek equals to row. Okay. Let me write sum over ek equals to rho.
Yes.
Okay.
Why don't it be? Because it satisfies the equation trace of sum over ek rho equal to 1.
It satisfies everything.
So,
Yes.
so then why you are taking sum over ek equal to identity?
Then this thing will be rho into rho, right?
Yes, rho is a pure state. Let us assume.
Then trace of rho square should be 1.
Yes.
So then rho is a pure state.
So if rho is a pure state, sum over ek equal to rho. So then why you are taking sum over ek equal to identity? So I
But
think
you have
one point is basically
no,
that
no, point is
we are
uh,
missing that is that equation. You should box it. That equation trace of sum over ek rho equal to 1. That is
this
the
one.
probability normalization. No, the second line.
Okay, this one.
Yes, you box it. It is coming from the probability normalization.
Yeah.
So that equation, you box it the whole equation equal to 1. It should be true for all row. It should
All
be
row.
true for mixed state also. So if it is
For
true
all
for mixed state also, then only one solution is sum over ek equal to identity.
Unless it will be less than 1, this rho square will be less than 1.
Exactly. That's why I'm telling.
Yeah.
I am
Yeah,
saying
that,
this example.
that is right.
Because
That is
this is the most interesting part that probability normalization should be equal to 1 for any state.
for any state. Yes.
For all state. Yeah. That's why
Right.
sum over ek equal to identity.
Or even you can make some, let's say some in this sum, some operator could possess negative value, right? Negative operator. If you introduce a negative operator, then you can actually this bypass this part. But now I will show that this operator cannot be negative even.
Yes.
Yes. So this is just coming because this probability of k should be greater than 0, greater than equals to 0. So I had this this one. So trace of ek rho. So trace of ek rho is greater than 0. From there I can take so from there, so trace of rho is positive already, so ek should be greater than 0. So these are my two conclusions. One is this one and second is this one. So these are the properties of POBM we have often encountered. So okay. So now see the form of the POBM. My form of the POBM was ek equals to pi pi ik, right? Let me give an example of such a POBM. We often write this kind of POBM. So let's say I have some P, say some E0 and E1. Let me write such POBMs. P into some 0, 0 plus 1 minus P into identity by 2. Realize this like this. So E0, let's say a 2-level system and you have 2 outcomes. So for pi 0, always you get in the ideal scenario, for 0, 0, you always get a detection in the up direction. And for similarly for 1, 1, you get a detection in the down direction. But this is not happening. So E0 is now my effective projector or POBMs. So this effective projector, I have written it like this, right? What I have derived now. Some probability into projector. So identity by 2 is also a projector, right? Extreme kind of projector. It satisfies all the properties of a projector. And identity by 2 is a very bizarre state. Any state you fed to this projector, or it will give you half. So this is like a noise. I mean, for any state, this projector will give you a probability half. So this is a kind of noise. So this particular projector is introducing the noise. That means some one particle can also go up. Now, realize this like this one. So this can also be written as 1 plus p. This is the general form, 0, 0 plus 1 minus p by 2, 1, 1. Just divide this identity by 0, 0 and 1, 1. Then you can write it. This is the very familiar form of spin POPMs. So see, these are the same form. So is this example clear?
Here you have taken a very particular example where each
Very particular.
P1 is equal to 1 plus P by 2 and P2 equal to 1 minus P by 2. That kind of example you have. But one
yes,
can construct more general spin POBM also.
more
like
general means
P1
by
0 0 plus P2 1
satisfying
1. That kind of
P1 0, 0
plus P2 1 1.
Right.
1 1 when P1 plus P2 equal to 1. Obviously.
But P1 plus
of
P2 should equal to 1.
Yes.
Yes.
One can construct that.
Yes.
Kind of.
So with this equation, for any probability, just you satisfy the properties of a projector, you will form any POBM. Like for any combination, it will give a POBM, a valid probability for the state.
Yeah.
So now I will elaborate this. What is happening inside that? So I begin with some scheme of measurement, how quantum mechanics is describing the measurement. There I have written a term, this one, and I said that I will come back to this. So now let us come back to that point. So this will be the current one is an intuitive understanding of POBM. So now I am restricting myself in quantum mechanics. I'm purely in quantum mechanical tools. So let's see what is happening. So how you can realize these POBMs. So let's say now my state is given by some C plus some psi plus C minus some psi minus. Okay. This is my spin state. So let me write psi s. And the same Stern-Gerlach magnet I will use again. And it has a position state, say some phi, which can also be written as some psi plus and phi plus. So if I give a unitary over here, like psi s, it is some x, let's say. So psi s cross this phi x, what it will be? I will again return to the same form I have derived. So it will be something like this, right? Psi plus some phi plus C minus psi minus phi minus. So my previous form was like this. Now I am just using it for a two-level system. As Saurabh was asking that for a general two-level system, what will be that? So I can write this like this, right? So associated with each spin degree of freedom, there will be a position state. I mean, a spin state and a position state. So let's say I write this like this. So this is my whole state after I evolve the state, the system and the spin degree of freedom and position degree of freedom. So now I ask the same question: what is the probability that I get a detection? So before that, let me draw a picture again. This is psi. This is my state, psi s. This is going. Let us consider it. Consider it like this. So this association phi plus and phi minus is this, but the detection wave function is some phi u. I am representing for up, and this is phi d. This I represent for down. So this is the difference. See, previously we have seen that associated with a spin, a state for spin degree of freedom, there is a state in position degree of freedom. So this association is given by this equation. Now, after this association, the state is detected on the screen, but I am assuming that this detection over the screen is given by some other wave function, phi u and phi d, right? In general, I should not assume that phi plus should be phi u and phi minus should be phi d, right? Because this entanglement between, I should not use entanglement because I have not introduced it here. So this association of phi plus and psi plus is happening inside after the interaction, but the detection, it is a incident that the detection is occurring on the screen. So I should not assume that always this position degree of freedom wave function will go up and minus will go down. So I have to assign different state for them in general. So I'm assigning that. So now if I ask the same question, that what is the probability that I get a detection in the up? So let me write. So P U, I am asking this question. What is the probability of getting a detection? So this will be what? This whole state by some projector like this, right? Because this psi is contain of 2 degree of freedom. So 4-dimensional system, you can say. So this is also a 4-dimensional system. So this one is a 2-dimensional projector. So I should associate some identity, right? Is this clear?
Yes.
This identity, yes, identity. This projector is for. So this projector is formed of like phi u, because I have assumed anyway this one. So this picture from this picture. So this projector is corresponding to the detection on the screen, not this association which we have discussed previously. Unless it would have been like some p plus equals to some phi plus. But I am not considering this because this will be an assumption then. Then I am saying that each of the position component is going up and each of the position component is going down. But there would be an experimental error, right? For that, I should not assume that. So I'm assuming that this projector is for the detection on screen up direction. So this is my projector. So if I write it, let's just write it explicitly. So my wave function was C plus this. Okay. So let me write it explicitly. So some C plus psi plus phi plus C minus psi minus psi minus phi minus inside this projector PU cross identity. Okay, so I am writing this wave function letter so that I should write this identity cross PU, right? Identity cross PU. Just I am exchanging this because I have written the system's wave function at the first place. Cross PU. Okay. And the same term, just you complement it and write it here. So what term will survive here? See, anyway, this psi plus and psi minus are orthogonal. So the cross term will not survive. Only the surviving term will be C plus mod square phi plus PU phi plus C minus mod square pi minus PU pi minus. Is this step clear? So I have multiplied the identity with psi plus and then I have taken the product. So only the same term will survive, like psi plus have survived and psi plus psi minus has not survived. So the the remaining term is only 2. It's clear?
Yes. Yeah.
Okay. Again, this psi plus, say C plus square. What is this? Anyone just tell me, what is this psi plus? I have this state, I have written here. So psi s was C plus psi plus C minus psi minus. It was my state. So what will be psi plus square?
It's the probability of obtaining psi plus.
Right. So it will be psi s into psi plus, right?
Inner product of psi s and psi plus.
And its square. Right. Is this right? Okay. So let me then put it over here. Then what it will become? So this will become psi s psi plus. Let me write it twice instead of square. Psi plus. Then it will be helpful for the calculation. So then psi plus phi plus then plus C minus. Similarly, I can write for okay. Sorry, this is not there. So phi plus PU phi plus, and for C minus also I can write that the same thing. Psi s psi minus, psi s psi minus, and phi minus PU phi minus. So this is my whole state now. Just I have substituted C plus for this. Okay. So these are the numbers, right? I can place it to anywhere. These are numbers.
Yes.
So let us have a slight manipulation then. Then psi s psi plus, let it remain here, and there was something phi plus, right? Phi plus, yes, phi plus p phi plus, and I can write it, say psi plus psi s, and similarly psi s, psi minus phi. These are all phi. Phi plus p, phi plus, and this psi minus psi s. So I can write this. See, psi s is there, psi s is there, psi s is here, psi s is here. So I can take psi s all over this operator residing inside. So let me write. So psi s and psi s. I'm taking it outside from the whole thing. Okay, and also this is also a number, right? These are also numbers. Then I can take this here. Then let me take it phi plus p, phi plus, and this psi plus plus this phi plus p. Oh, this was phi minus. Right. This was phi minus. So anywhere, if you get any confusion, then just tell me. So phi minus, and this will be psi minus, and this state is now I am writing it here. Psi yes. So this is now the whole probability becomes like this. So see, some number times some projector, some number times some projector. And this projector, see, this projector is psi plus and psi minus. That was my spin eigenstates. Psi plus and psi minus, not the position. And this is just a probability or just a number. So some number times some projectors, and then some number times some projectors. So do you find any resemblance or with the previous one? There is some resemblance. That some previously in the definition of POBMs we have written probability time projectors, and those projectors were for spin components. Here we are getting the same one. So let me write then psi s. I define it by some EU psi s. So what is the EU? EU is this whole thing. Some pi plus p, pi plus, some projector pi plus. I can now write this one to be pi plus, and then pi minus p, pi minus, this pi minus. This is now very important, this form of this of POV. And similarly, I can also calculate E down, E for down. Just you replace this, or you can just identity minus EU. You can take. Oh, okay. Somewhere I have missed this EU, so that I was not finding this. So EU is there already. So just replace this projector by PD. So you will get this one also, ED. So now look at this thing. So as I have said, if phi plus was phi u, then what was that? That was a perfect detection. So if say phi plus is phi u, right? Then what I will get from my equation? Then PU will become 5 plus 5 plus, then this whole term will become 1 and this term will become 0. Then my POVM will become this projector and I have an ideal measurement. That means this unsharpness in the measurement is coming from the fact that the detection, so according to von Neumann, this detection pointer is a quantum device. So if I associate a quantum wave function with that, and if I associate another wave function to the position degree of freedom of the state, then these do not have a one-to-one correspondence. That means always phi plus is not going up, it is sometime going down. This is the reason why the unsharpness is coming in the measurement. So if this phi plus was phi u, then we would have 1 and this is 0. And similarly, for the other case, I will have this term survived and this is 0. And now you can associate it with your previous derivation. Like previously we had some probability times some projectors. 1 minus p times some p pi minus. So this probability is actually coming from this. So this contains the error part of the measurement. That some particle should go down, but it is going up. And some particle should go up, it is going down. So that probability, if we can calculate, this is the unsharpness of measurement. So there are debates whether this origin of this unsharpness is quantum or classical. There are various debates. But for now, we can see that this origin is completely quantum, at least with this derivation. So is it clear for now? Hello?
Yeah.
Okay. Okay. So how can you quantify this? Let me define a quantifier. So let us assume this is the quantifier. This is the fineness. So let me draw again the same picture. So in the screen, I am now drawing the screen. In the absence of magnetic field, it was in the middle. So it is say x equals to 0. This point. And this is the x variable over this position. So I get some peak like this. So these outcomes are normally distributed, but some up are going down, some down are going up. So there is a certain overlap in this region. So this is the origin of the unsharpness. So intuitively, then how can I define a measure? So this, as I said, that if your phi plus was phi u, then you have a perfect detection. Then 0 to infinity means this is 0 and this is for say infinity. So 0 to infinity, I can define such a measure. So let's say phi plus and phi up should be same. If it was same, then it should be 1. Then I have a perfect measurement. But for the imperfect measurement, this is not coming 1. So it is less than 1. So this is then the measure of fineness or sharpness here. So as this d approaches to 1, we will have a more perfect measurement. So dx is the variable. Okay. 5 is a function of x, you can write. So any question?
So somehow it is related to that small g, right?
Yes.
Because
Certainly.
that small g determines whether this overlap will be there or not. I mean,
Right.
your measurement will be sharp or unsharp. That will determine by that small g.
By that small g. Yes. So if you can calculate what is the sufficient value of g for that this overlap vanishes, then you can set up a arrangement, I mean experimental arrangement, so that we will go towards more ideal measurement.
Okay.
Okay, so these are the, I mean, two ideas I wanted to describe, like how to visualize this unsharp spin POV, because we often use this unsharp spin POV. The form of like 2-3 general forms are there, but where they are coming, this is the origin. This is how you can visualize these spin POVMs. So I have time? Okay. Then let me discuss a bit more. Okay, so let me discuss from another perspective. So now you assume that your this up and down, what I was saying, this up and down state position, which is in position degree of freedom of the screen, up p phi u and phi d, after the detection, the state actually disappears, right? So like it has interacted with the environment and it declared something like this. So these detector states can be treated as a environment that is related to the system. So if I now concentrate ourselves in these two systems, one is my spin system that is defined by rho s, and this environmental system, this is given by some rho environment. This is my whole system. Okay. So if I now want to find only my system, what I can do? So rho is dash. So in the interaction, it will evolve, and I can find. So let's say I can in the interaction, it will emerge as some rho dash. For generality, I can associate. Oh, sorry. So rho s cross some rho e times u trigger. I can write it after as I consider this to be a system, this to be an environment coupled to the system. So after the say this u is giving the interaction term. So I can write this. So how can I sort out this system from this after it evolved? So it will just, I can take a partial trace over the environment, right? So as you know, I assume that everyone knows this, how to take partial trace. So unless I'll just tell rho s cross rho e identity. So this is my whole thing. So in the partial trace, what we really do is that we have state vectors in that environment, the complete set. We just take inner product over all the basis vectors of environment. So let me do this. So So that will be environmental state will be what? Some phi u. So u rho s cross rho e u trigger phi u plus phi d u rho s cross rho e u trigger phi d. This will be my state. And if I assume for generality, let's say environmental, so this environment is in a some pure state. So then u rho s cross something say some psi I. The whole state I'm writing down. I can assume it to be a pure state. So u trigger phi u and also phi d u rho s cross psi u trigger phi d. Okay, so this is my whole thing. So see if I so this unitary is over the whole thing, the environment and the system. So if they have 2 dimension like 2 and 2, so unitary will be 4 dimension, 4 cross 4 matrix. So then what can I write? I can write phi u psi I. Can I write this? Rho s psi I to trigger psi u plus some psi d u psi I rho s psi I trigger psi t. So this I can write, right? So see, this is 2-dimensional Hilbert space, and this is 4-dimensional. So this whole thing is not a number. This is operator. Similarly, this thing also, this one. So then I can write it as an operator. And m rho s m some m dragger. Say m1. It is m1 plus something. Say m2 rho s m2 dragger. I can write this. So now, after I evolve the state, I have found the state of the system. Now, if I ask what is the probability of a detection at k, so then what will be that? So now I am associating a projector of the spin degree of freedom. So this then I can write, this is some mi rho mi rho mi so pi k anyway I can take it to here, right? Mi, so rho is the state, so mi in the trace I can do this operation, right? Mi into rho. So again, see, we have arrived to the same type of probability, like the form of this whole thing is the one we have encountered before also. If I associate some operator with this, then it has the same function. So let's say I write the same thing like mi pi k mi dragger. So this mi pi k mi dragger is ek. Then again my probability of k is becoming ek into rho. Then this is my POVM. This is same as my POVM. Then see, ek is what? Ek is some operator evolved projective valued measure. These operators are called, in quantum information theory, these operators are called Krauss operators. So I can say then the POVMs are actually Krauss operator evolved projective valued measures, or PVMs. So the Krauss operators contains these kind of things. So what are they? One is phi u, one is psi I. So this is a function of the environmental degree of freedom, the position, and also the spin degree of freedom. So it is kind of a interaction term, like a operator originating from the interaction of the spin degree of freedom and the position degree of freedom. So this is a kind of Krauss operator. We often call it like this state has evolved through a channel. We also call it a channel after this, after the state evolved through such a thing. So like a projector is evolved through a channel to become a POVM. So this is the conclusion. So do anyone have any question? Hello? Hello?
Hello.
Yes.
Mhm. Yes, yes. So anyone have any question? You can directly ask. I cannot see the chat box, so anyone can
No,
ask.
there is no question in chat also.
Okay.
Sumit, I have a question.
Yes, yes.
Now, you have done that calculation very beautifully. I mean, I really appreciate it, that I have not observed it before in that way. Anyway, so let's say the whole motivation of doing this, let's say you are not getting two distinct two distinct distribution in your screen. That's why you are doing this exercise, that what is happening in there, and there your conclusion is that the projection operator itself evolving in the Krauss formalism. That's why you are not getting the distinct distribution in the screen. You are getting a overlap distribution.
Right.
Now let's say I have a state which is itself is not a pure state, which is itself a state is a, let's say, A0 plus B1 and with white noise in it. I mean some I/2 mixedness in it. So that kind, the famous example is the Warner class of state. So if you again do the projective measurement on Warner class of state, you will still get that overlapped version, right? I mean, then one can also tell, okay, projectors are not evolving, but the states are evolving.
Right.
Are
in
they
that
equivalent concept? I mean,
that I have not checked, but maybe like this is like a relation of Schrodinger's picture and Heisenberg picture, like whether the projector is evolving or state is
evolving.
So this is a good question. So I have not investigated it. Maybe we can show if they are equivalent or not.
Okay. So there is a possibility of doing some work in that direction.
In this direction.
Okay.
And also, what kind of Krauss operator is this exactly? Like the known one, whether we can do like amplitude damping channels and this,
right.
channel. Yes. And so that I have not investigated.
Another question is, whatever you are telling, okay, we have done some measurement. So let's say I take one case where I am doing nothing. So how can
Okay.
I formalize this concept? I mean, let's say I have a coin, okay,
Okay.
and whenever the coin outcome is head, I am doing the projective measurement, and it may be a noisy projective measurement, or it may be a ideal projective measurement. And when I get tail, I do nothing. Then what kind of picture you can think of in this language?
So then means you have some coin. When you get head, you are doing a projective measurement.
Yes.
And when then you are doing nothing.
Yeah.
Nothing means identity. Then then you can just write this like this, say some P1 into some projective measurement, say some pi plus identity into P, maybe this kind of thing will appear. Oh, that is that is okay. That is a, you are mixing two things classically. Like, so you are tossing a coin, and if you get a head, you are measuring something, some observable. So projector I cannot measure. I am measuring some observable, getting some result associated with that. I have a projector in quantum mechanics.
Yes.
So then I should write P into M1 plus P2 into identity, maybe, because P1 times you are doing some M1 measurement and P2 times some identity. It should be then represented
So,
like this.
okay, so
But this is a classical, like this error is like hand given, right? Like you classically putting this error into the measurement.
Right. So in that way, in your previous, you are telling whether this kind of answer measurement is quantum or classical. There is a debate. So I think classically also one can achieve this, right?
Yes. Like the first example, what I was giving, the first one. So this PI,
Yeah. Yes.
it is a classical PI, right? So
Yes.
this is even I mean, this question is still in my mind. So, but the latter one, the origin was completely quantum mechanical, but we are getting the same form of probability distribution and same form of POVMs. So whether I can replace this quantum origin by some classical origin. So this is a valid question, and maybe very deep question. So with both the formalism, you are getting the same thing, right? Here I have not used any quantum probability. Like I don't have a quantum random number generator here. I mean, a classical probability suffices for this treatment. So that question should be asked.
And let's say if your PIs, then will there be any effect? I mean, let's say this, you are taking the superposition kind of thing. Here it is a convex mixture kind of thing. You are
Convex
taking, that's
mixture.
why you are interpreting PI as a classical one, because you are taking convex mixture only.
Convex
But
mixture, yes.
let's say somehow we make some superposition in it, and it comes from bond rule probability. Then will there be any peculiar effect or no?
Maybe
I
some
don't know
peculiar
whether this question makes sense or not.
Maybe we will get some peculiar effect. We will then replace this PI by some probability coming from quantum theory.
Exactly, and maybe we can see more deeper thing in quantum theory itself, the measurement process.
Right.
Because in any way in the lab, people will not see the distinct distribution. It is very difficult to achieve this. So in a more operational oriented way, you will always see some kind of overlap between these two distributions.
Right. So this is like two ways of explaining how to visualize POVM. So people may think some other ways of explaining POVM. Like 2-3 ways I have just discussed today.
Yeah.
So this is one way. The second way is this from this picture using quantum mechanical tools. Another way is by using channels, like you treat your environment to be the screen is your environment and all. So these are some ways, but at the end of the day, because it is a like semi-definite matrices, you are getting the same kind of form like this one. Probability of, because at the end of the day, what you observe, that is the probability of certain outcome. And if you are getting the same thing, then maybe these different way of thinking is actually equivalent, maybe. So this is actually a question, whether
that
they are
means
really equivalent or
your-
some.
POVMs are equivalent. I mean,
Mhm.
same, but the how you realize that POVM, that makes it interesting.
That may, yes, right. And whether in some information processing task you can distinguish this kind of different thinking, like in one formalism that cannot, I mean, reflect into the something like that.
Oh, it's a very nice point you have made. That will there be any quantum information processing task such that we can differentiate between the
Between
realization of two POVMs?
two PAVMs, right?
So, okay, so that is very good question.
Maybe then someday, if one can do, then one of my, one of my procedure will be discarded then.
Okay, okay. Okay, people can do in future, right? This kind of research, that finding some information processing task, that will be a valid direction, right?
Yeah, that will be a valid direction. Yeah. So anyone have any other questions?
I have two questions. So
Yeah.
can you hear me?
Yes, I can hear you.
And thank you for your tutorial. It's very informative. So do you have any plans to consider homodyning, heterodyning measurements for continuous variables?
Okay, actually, so I don't know these terminologies like homodyning and heterodyning measurement, how they are performed. So if you can just tell me in brief what they are, then I can say something about this.
Okay, I will try. Second question, and also quantum tomography. So I think this is also part of quantum measurement, right? I'm just asking whether you are going to consider or not. Yeah. Okay.
In quantum tomography, so in quantum tomography, what is the precise question? So quantum.
Yes, in quantum tomography, you can also do the measurement technique. So,
to do quantum tomography, you have to do a quantum measurement.
Yes, you have to rotate your reference frame by some angle.
That is for a like tomography, you can measure in like all the MUV direction to infer a state. So what is the question then?
Yes. So are you going to consider also the quantum tomography? Not now, maybe.
In what context I should consider, like that I'm not getting.
The topic of your tutorial is quantum measurement. So in measurement, are you also considering quantum tomography?
So okay, so I was describing them like how you can realize a measurement. Anyway, those measurement POVMs and its properties were there from before. So I was just describing how you can realize these POVMs physically. So what are the different procedure you can take? But in tomography, I don't think there is a link, because you already have quantum mechanical tool. You don't need any other things to do a quantum tomography.
You see,
even if you don't realize POVMs like this, what I have said, you can then also do a quantum tomography, right?
I just want to add a point regarding the tomography. So quantum tomography is a very important property of any theory. So in your theory, the measurement, there should be some measurement procedure that will give the power of tomography. Now, to do a tomography, you need to have a special class of POVM. Not all POVM will give you the tomography, and that special class is called
informationally
POVM class. SIC POVM class. That is informationally complete POVM class. So
Right.
if you measure in informationally complete POVM domain, then quantum tomography is possible. I mean, not possible. That is the need for do the quantum tomography.
Hmm, hmm.
The
So,
process of realizing those measurements can be found what Sumit just discussed. The process will be same. That
Right.
you will have a spin system, then you have to correlate with a pointer state, and then you do the measurement in the pointer state basically.
yes, because what you have showed is very fundamental and very useful, but it will not like reconstruct the off diagonal elements, because off diagonal elements will contain phase, but
Off diagonal elements of what?
density matrix. So in case of
So
diagonal
I mean, the quantum probability is distinct because it has a off diagonal element in the matrix of rho, right? If you just discard all the off diagonal element, you cannot get any quantumness from the system, right?
no, you will get the elements of the diagonal elements what you have shown, but to get the elements of off diagonal, then you have to consider phase, because what you have shown, that is the modulus of the probability, right?
Okay, so
it means
while writing the four terms, I have discarded two of them because they were off diagonal. Yeah, are you saying for that?
What I'm saying, any number, I mean the complex number, it has two elements. One is the module of that complex number, and then the phase. So when you are doing the measurement, what you have shown, that will from that you will get the modulus of the complex number, but not the phase value. And the phase value you will get by doing quantum tomography or maybe some other technique. So in that way, okay. So the last question, what I wanted to ask or request you, could you please suggest references for self-educational purposes uh, on the topics covered by you today?
Okay, yeah. So those I can write it over the screen maybe, or I can tell you just. So that is like Paul Bush's paper. You can just note it down. One is Paul Bush's 1985 paper that is called Unsharp Reality. The paper's name is Unsharp Reality. So you can search that. That is the first paper maybe that has introduced this unsharp measurement. And if it seems complicated, then you can take reference from a book that is maybe published in 2002. That is by Paul Bush and Pekka Lathi. And some other references I can give. Some you can see some papers by Ravi Kunjwal. That is some PRA papers published in 2014 and 15 in this tenure, which have discussed this unsharp measurement, and some papers by Haniswari and all, Haniswari and Ojawa. So there you may, if you are interested like this information disturbance trade-off relation, which I have not covered today. So those things are also take part in this kind of discussion. So for that you can see some of Ojawa's paper and some of the papers by Haniswari.
Okay, thank you. Could you please share your email address? That will help, I think, not only me, to all of us. If something is required or consultation is required, we can send you a message.
Yes, sure. So should I write it on the chat box? So yes, let me write it in the chat box.
I think then the Paul Bus's 95 paper, the quantum measurement book is very good actually.
Book is
95
very good.
paper,
That's-
the notations are really old and that.
yeah,
But
that's why I was
when they
telling you.
wrote the
One may,
quantum, two books are there actually, one on quantum measurement and one on the operational quantum theory. That
this,
kind of.
yes, right.
So these two books are very.
Please repeat once more the name of
One of the book name is just quantum measurement, and
Mhm.
authors are Pekka Lathi, Pelenova, and Bush. And
Okay.
another book is the exact name I'm telling you. Just give me a second. Another name is like the operational framework for quantum measurement. That kind of name. I'm just checking and I'll tell you.
Maybe the operational formalism of quantum measurement, maybe something like this.
Okay, thank you.
Yeah, so their book is actually very good. This Pekkaladi Paul Bush's book, compared to the old paper.
Because they
Thank you.
really systematically formalize the concepts and also
Because-
that how much disturbance you should make to extract some information about the state. Because doing tomography, that is very important, that how much disturbance you want to make and what kind of information you want to take into account.
Thank you. Thank you again for delivering a very informative tutorial. Thank you.
Thank you.
Is there any other questions? Shubinda,
Yeah.
could you please write those all reference in chat box? Then it would be helpful to other members.
Okay. So Rudita, you can also write to like the references you are saying
Yeah,
Okay.
one I am posting.
in the chat
This
box.
one.
You can
Yeah.
write.
I have posted one. I'm searching for another one. Yeah, one is quantum measurement and another is operational quantum theory. Both books are written by Paul Bush and his student Kalati.
Okay, you are giving the link. Okay.
Yeah, I have given the link.
Oh,
I do not
Lisa,
see that there is another question, I think.
okay.
So we are concluding our session here.
Okay, thank you.
And thank you again, Shweta, for the beautiful tutorial session. And all participants are requested to attend our next talk, which will start from 7 p.m. And our next speaker is Stephen Gilvin. So we are expecting a large number of attendants. So all participants are requested to attend the session. Thank you. See you next talk.